Welcome to this webinar on computational blood flow, which focuses on the modeling of pulse wave signals in human arteries and on the clinical value of modeling and analyzing pulse wave signals. I'm Alastruey, a senior lecturer from the Department of Biomedical Engineering at King's College London in the UK. In the hemodynamic modeling lab that I lead, we study blood flow in the cardiovascular system using clinical data and a combination of computational and experimental modeling. Our broad aim is to develop methods for cardiovascular function assessment based on the analysis of pulse wave signals. These signals are produced by the pumping of the heart, which distends the wall of the aorta, generating a distension wave of the arterial wall, which is called the pulse wave, that propagates through the arteries. The pulse wave leads to a rhythmical expansion and contraction of all arteries, for example, producing the pulse that we can feel in the wrist. This pulsatile movement of the arterial wall produces changes in blood pressure and blood flow with time and space throughout the arterial system. For example, invasive measurements of blood pressure with time along the aorta every 10 centimeters from the root next to the heart and up to the bifurcation of the aorta with the two leg arteries show that there are several features in the pressure signal that are produced by the propagation of the pulse wave, either from the heart to the periphery, an example being the early rise in pressure at the start of cardiac contraction, or pulse wave propagating in the opposite direction, due to early reflections coming from peripheral arteries, an example being the shoulder before peak pressure. Why do we want to model and study pulse wave signals? These signals can be measured in vivo using a variety of devices and are influenced by the cardiac and vascular systems, making them a rich source of information on cardiovascular health. That means that pulse wave signals carry valuable information on cardiovascular health. Here you can see some examples of different clinical devices that can be used to acquire pulse wave signals in different positions of the body. This is the outline of this webinar. I will start by talking about arterial pulse wave modeling, and after I will go in details through a few projects that demonstrate the clinical value of pulse wave modeling and analysis. When it comes to arterial blood flow modeling, there are three main modeling approaches: three-dimensional, one-dimensional, and zero-dimensional models. They can all describe time-varying blood pressure and blood flow in the cardiovascular system, but with a different degree of accuracy in space. 3D models account for the variation in pressure and flow in the three-dimensional space. 1D models only consider changes in pressure and flow along the axis of the vessel, and 0D models are space independent. That makes 3D models more suitable for describing local features of blood flows, whereas 0D models are more appropriate to describe global features. However, 3D models are computationally very expensive compared to reduced order models, taking of the order of hours, even days, to compute the solution using high-performance computers. When it comes to simulating the effect of the propagation of the pulse wave on blood pressure and flow, we use the 1D formulation, since it is a good compromise between accuracy and computational cost, taking of the order of a few minutes to compute on a standard PC. In the 1D formulation, the arterial network is decomposed into arterial segments connected to each other at nodes. Each segment is simulated as a thin, deformable tapered tube whose properties can be described by a single axial coordinate x. Then, using the physical principles of conservation of mass and momentum, and applying the list of modeling assumptions on the right, we obtain a system of partial differential equations that govern blood flow in each arterial segment. The variables of the problem are the cross-sectional area of the tube, A, blood flow velocity, U, and blood pressure, P. The third equation is called the tube law and relates changes in blood pressure to changes in cross-sectional area, taking into account the material properties of the arterial wall, such as the Young's modulus, which is a measure of arterial wall stiffness. We solve these governing equations for each arterial segment using an in-house finite element method. The first two equations were proposed by Euler in the format you see below. It is curious to note that in explaining the motion of blood, he mentioned insuperable difficulties that impeded us to accurately represent the work of the Creator in all its splendor. And it was thanks to Riemann that we were able to highlight the wave nature of the 1D governing equations. Riemann's method of characteristics is a mathematical analysis that allows us to show the existence of pulse wave propagating from the heart to the periphery and back to the heart. The analysis can be applied to the three governing equations on the left, without the viscoelastic term in the tube law. In that case, the governing equations are for a purely elastic arterial wall, and they form a system of hyperbolic partial differential equations, so they are wave equations. Using the method of characteristics proposed by Riemann, we can transform this system into a set of advection equations that are shown on the right. These equations are for the variables WF and WB, which are the forward and backward characteristic variables. The two advection equations on the right top are weakly coupled, since the source term S is much smaller than the terms on the left-hand side of the equal sign. These two advection equations indicate that changes in pressure and velocity propagate with a speed u plus c in the forward direction and a speed u minus c in the backward direction, where u is the speed of blood and c is referred to as the pulse wave speed, which depends on the elasticity of the arterial wall through the beta parameter that appears in the tube law on the left. The movie shows the propagation of a short pulse wave in a single arterial segment with a complete reflection at the outlet. Note that WF is associated to changes in pressure and velocity in the forward direction, and WB to changes in the backward direction. We use the characteristic variables when prescribing the boundary conditions at the inlet and the outlet of each arterial segment. Going back to the slide on the invasive blood pressure along the aorta, we can now better understand that the pressure signal is shaped by the propagation of the pulse wave, either from the heart to the periphery, an example being the early rise in pressure at the start of cardiac contraction, or in the opposite direction due to early reflections coming from peripheral arteries. The speed of propagation of the pulse wave is about 6 meters per second, which means that during a normal cardiac cycle, which takes of the order of 1 second, the pulse wave has sufficient time to travel multiple times from the ascending aorta to the periphery of the arterial vasculature and then back to the aorta. So far, we have seen how to simulate blood flow in an arterial segment. To simulate blood flow in the arterial network, we need to connect 1D model arterial segments at arterial junctions. We solve the junction problem by enforcing conservation of mass and energy and ensuring the correct propagation of characteristic variables across the junction. And as for the boundary conditions of the arterial network, at the root of the ascending aorta, we prescribe the flow waveform ejected by the left ventricle as inflow boundary condition. This waveform can be measured, for example, using phase contrast magnetic resonance imaging or Doppler ultrasound. We can see that in systole, the aortic valve is open and blood flow is positive. In diastole, the aortic valve is closed and blood flow is approximately equal to 0. What about the outflow boundary conditions? Each terminal branch is coupled to a 3-element Wien-Kessel model which simulates the resistance to flow and flexibility of downstream vessels. The former is simulated by a resistance R and the latter by a compliance C, which is defined as the change in blood volume per change in blood pressure. As with any model, the next step is to assess the model accuracy. So how accurate is 1D, 0D modeling? To answer this question, first we compare simulated pressure and flow waveforms against measured data in a 1-to-1 scale model of the systemic circulation made of silicon tubes. In the middle of the slide, you can see a plan view schematic of the experimental setup. The thicker tube, which represents the aorta, is connected to a pump simulating left ventricular contraction, and each terminal branch is connected to peripheral resistors. In this experimental setup, unlike in the human body, we could be as invasive as we wanted when measuring physical properties. We measure all the input parameters to the 1D formulation: the length and diameters of all arterial segments, the material properties of the silicon that was used to simulate the vasculature, namely the Young's modulus and the viscosity, the density and viscosity of the fluid used to mimic blood, the inflow boundary condition at the aortic root, and the parameters of the outflow boundary conditions at each terminal branch. We also measured blood pressure and blood flow in over 70 points in the silicon network. We then ran the 1D model to obtain simulated pressure and flow waveforms in the network of silicon vessels. And we saw that the numerical predictions for pressure and flow waveforms in dashed lines were able to approximate corresponding experimental waveforms in solid lines, with average relative root mean square errors smaller than 3% in pressure and smaller than 11% in flow rate for all points. The plots show comparisons for blood pressure and blood flow wave at 2 points in the silicon network, the right carotid artery and the thoracic aorta. We have also verified the accuracy of the 1D formulation against pressure and flow data simulated using the 3D formulation in several idealized geometries of the aorta and other large systemic vessels. The 1D geometries were obtained from the center lines of the 3D model, and the diameters and wall thicknesses of the vessels were identical. The 1D and 3D formulations also shared identical inflow and outflow boundary conditions and had compatible material laws. First, we compare pressure and flow rate with time at the inlet, midpoint, and outlet of the idealized common carotid artery, which we simulated as a straight and uniform tube. The red lines correspond to the results given by the 3D model, and the dashed black lines to the 1D model. The color maps at the bottom show the velocity magnitude given by the 3D model at 2 time points, during flow acceleration at the start of systole and flow deceleration towards the end of systole. Superimposed, we compared the velocity profiles for the 1D and 3D models at 3 locations. The results show excellent agreement between the two models. In the aortoiliac bifurcation, we also found a very good agreement between both formulations, with similar relative errors to the common carotid model. And here you have the results for a model of the full aorta. Flow rate wave on the left and blood pressure wave on the right. You can see in blue the results from the 3D model, in red the results for the nonlinear 1D model, and in black those for a linearized version of the 1D model. Using 1D modeling, we obtain average root mean square errors relative to 3D model predictions smaller than 3% in both pressure and flow rate. We have also tested the accuracy of 1D modeling by comparison against in vivo data acquired in the upper thoracic aorta by magnetic resonance imaging. Flow waveforms were acquired using gated PC MRI, and area waveforms were obtained using gated 2D Cine SSFP MRI, which provided dynamic area images on the same 5 planes as the flow waveform measurements. We also acquired blood pressure in the carotid artery by applanation tonometry. In this study, we had to reduce the number of arteries to have a truly subject-specific model. We were able to show that it isn't necessary to have a large number of arterial segments to capture the main features of blood flow and area waveforms. We obtained average relative errors smaller than 7% between simulated and in vivo flow and area waveforms. We didn't have invasive pressure measurements in the aorta for this study, but the area waveform measurements are a good surrogate for pressure waveforms. And later I will show you comparisons between in vivo and numerical blood pressures at the aortic root. These verifications against experimental, in vivo, and 3D generated data have given us, and also other research groups, confidence in using 1D modeling to simulate pulse wave signals and tackle clinically relevant problems. Central pressure assessment is the first project in collaboration with medical doctors that I would like to show you. The aim of this project was to estimate central blood pressure using non-invasive input data. Central blood pressure is the blood pressure wave measured in the aorta next to the heart, and hence it is the load that the heart has to overcome when it pumps. We want to estimate central blood pressure because it is a highly prognostic cardiovascular risk factor. For example, an increase in pulse pressure, this is the amplitude of the pressure wave, leads to hypertension, which is the single most important cause of morbidity and mortality worldwide. And several clinical studies have shown that central blood pressure has a higher prognostic value than peripheral blood pressure, measured, for example, in the arm by the GP. We want to have a non-invasive methodology to estimate central blood pressure because at the moment it can only be measured directly by catheterization, which is costly and has associated risks due to its invasive nature. We have developed a methodology to estimate central blood pressure from non-invasive clinical measurement using 3 types of reduced order models with increasing complexity. This can be seen in the column on the right. We have 2 0D models and the 1D model of the upper thoracic aorta that I showed you before. The input data on the left is the blood flow pumped by the heart into the aorta, measured by either Doppler ultrasound or PC MRI. The blood pressure measured in the arm using a standard pressure cuff. And for the 1D model, we also require the anatomy of the aorta measured by MRI. From this input data, we can estimate cardiac and vascular parameters that are then fed into the 0D or the 1D models to produce the desired central blood pressure as output. I have already described the 1D formulation that is used for the 1D aortic model, and next I will describe the 3-element Wien-Kessel model. The 3-element Wien-Kessel model relates aortic blood pressure, P, to aortic blood flow, Q, with both P and Q being functions of time only. The parameters of the model are 2 resistances to blood flow, ZC and R, a compliance, C, which accounts for arterial distensibility, and an outflow pressure, P out, which is the pressure at which blood flow ceases. The model can be represented using an electrical circuit because of the analogy that exists between the flow equations and the electric transmission line equations. Blood flow and pressure are analogous to electric current and potential, respectively. Fluid resistances correspond to electric resistances, and arterial compliance is matched by electrical capacitance. Using electrical circuit theory, we can obtain this ordinary differential equation relating blood pressure to blood flow, which can be solved for blood pressure as a function of time using the integrating factor method. The input data that we had to calculate the model parameters were the aortic blood flow waveform, QT, aortic pulse wave velocity, PWV, blood density, ρ, and peripheral mean and diastolic blood pressures. The equations below were used to calculate the parameters ZC, R, C, and P out from this input data, so that we were able to calculate aortic blood pressure from aortic flow. Let's move on to the results. Here I'm showing in red estimated central blood pressure wave using the three-element Wien-Kessel model, compared to reference measurements in blue for normotensive subjects at the top and hypertensive subjects at the bottom. Although the model does not accurately reproduce fine details in the pressure waveform, pulse pressure is reproduced accurately. And the pulse pressure is of particular importance for hypertension, so we focus on assessing errors for the pulse pressure. We did this using statistical methods that are popular within the medical community, such as Bland-Ullmann plots. In case you are not familiar with Bland-Ullmann plots, these enable the analysis of the agreement between two different methods. For example, a new method and the gold standard one. Differences between the two measurement methods are plotted in a scatter diagram against the values obtained using the gold standard method. In our case, the y-axis shows the difference between measured pulse pressure values and the estimated ones, and the x-axis shows the measured pulse pressure. Horizontal lines are drawn at the mean difference, these are the solid lines in the plots, and the limits of agreement, these are the dashed lines, are usually defined as the mean difference plus and minus twice the standard deviation of the differences. There are three plots because we used three groups of subjects for this study. It was very helpful to first design and optimize our algorithms using a large in-silico database of pulse wave before doing the final testing using real clinical datasets of normotensive and hypertensive subjects. And later I will explain how we generated the in-silico database. The three Bland-Ullmann plots indicate that we obtain reasonable errors for a wide range of pulse pressure values. In normotensive subjects, normal physiology was perturbed using vasoactive drugs with divergent effects on the heart and arteries to cover a wider range of physiological pressures. We went further than just proposing an accurate method for central pulse pressure calculation. The three-element Wien-Kessel model also allowed us to investigate the physical determinants of increased pulse pressure in hypertension in a subject-specific way. Of particular clinical interest is the quantification of the relative contribution of arterial and heart properties to the increase in pulse pressure. We found that high dynamics accounted for more than 50% of the increased pulse pressure in hypertension. So cardiac dynamics are quite important, even more important than vascular properties, which is contrary to some common knowledge. This is important because current antihypertensive drugs focus on altering vascular properties, but our study suggests that cardiac properties should also be involved in the treatment strategy. The Central Pressure Assessment Project has greatly benefited from using in-silico pulse wave databases. Indeed, developing and testing pulse wave analysis algorithms requires comprehensive datasets measured in large clinical cohorts. Unfortunately, acquiring these datasets is usually an expensive and time-consuming task. To facilitate this process, we have created, using 1D modeling, databases of simulated pulse wave representative of a sample of healthy adults. The last one that we have created, and which I'm going to present here, contains several types of pulse wave at common measurement sites for over 4,000 virtual subjects, aged 25 to 75 years old. So how were virtual subjects generated? Firstly, 1D modeling was used to simulate pulse wave signals at a range of measurement sites where pulse wave signals can be typically measured in real humans. The cardiovascular properties of this model were obtained from the clinical literature for a 25-year-old healthy subject. Going from left to right, we simulated the following signals: blood pressure, blood flow velocity, luminal areas, and PPG signals. In real subjects, the PPG signal is obtained by shining a light onto a tissue, such as the finger, and measuring the light which is either transmitted through or reflected from the tissue. And this varies with time as the volume of arterial blood in the tissue changes. The attenuation of light due to the non-pulsatile venous blood and other tissue components is relatively static, so that the pulsatility of the PPG signal can be assumed to be entirely due to arterial blood flow. In this study, the PPG was modeled by calculating the volume of blood stored in the terminal wing vessels as a function of time. The second step to generate virtual subjects consisted of performing a very comprehensive review of the clinical literature to determine which input parameters to the model change with age. We identified the 6 properties on the left that change with age. The numbers between parentheses indicate the number of articles we look at for each parameter. For each property identified as changing significantly with age, we extracted mean and standard deviation values across age groups from the clinical literature. Mean values are shown in solid lines and standard deviations in dashed lines. A baseline subject at each age at each age decade from 25 to 75 years was then created using the age-specific mean value for each property. So for example, the baseline subject at 45 years old has the heart rate value circled in red. Pulse waves were simulated for a set of subjects at each age decade by changing the 6 identified cardiovascular properties in combination with each other by plus and minus 1 standard deviation from their age-specific mean values. This resulted in 3 to the power of 6, which is 729 subjects at each age, and a total of 4,374 subjects in the database. Simulated wave at different age groups shows similar changes with age to those measured in vivo. Here you can see the comparison for blood pressure measured in the femoral artery. It is remarkable to see that the simulated diastolic peak disappears gradually with aging, as observed in vivo on the left. What is even more remarkable is that when we compare simulated hemodynamic characteristics across age groups with corresponding in vivo ones from populations of real subjects, we found that the trends and even the values were similar between the two. It is important to note that the 4 characteristics on the slides, which are examples of hemodynamic characteristics that we look at, were calculated from the simulated pressure wave signals. They were not imposed as input parameters to the simulation. Aortic systolic blood pressure is the peak blood pressure at the ascending aorta. Brachial mean blood pressure is the average pressure at the brachial artery in the arm. Pulse pressure amplification is the ratio of the amplitude of the brachial pressure to the amplitude of the ascending aorta pressure. And augmentation index is the change in pressure from two characteristic points of the pressure waveform in systole. Some of the hemodynamic characteristics were calculated from the simulated signals using pulse wave analysis, which enables identification of fiducial points by calculating first, second, and even higher order derivative of the pulse wave signal, and then calculation of indices from these points. We believe that this in-silico dataset, which has been funded by the VHF, is a resource that will be widely used by researchers that want to develop new pulse wave analysis indices. This project is not about patient-specific modeling, but rather population-specific modeling, which enables a preclinical design and assessment of pulse wave analysis techniques across a wide range of cardiovascular conditions in a relatively quick and inexpensive manner. It has the advantage of knowing the exact cardiovascular properties which generated each pulse wave for each virtual subject. For example, the central blood pressure that was used in the central pressure assessment project I showed you before. And once the paper describing in-silico database is published, we will make the database publicly available. Here you have more examples of recent studies, some of them are still ongoing projects, that have benefited from using in-silico datasets in the algorithm development phase before testing using in vivo data. They all use pulse wave analysis to estimate properties related to cardiovascular function. I have previously talked about the first project, the estimation of an assessment of central blood pressure from aortic flow. The second project involved cardiac output, which is the amount of blood pumped by the heart per minute, and which is a critical measurement in intensive care medicine. Algorithms for tracking cardiac output from non-invasive blood pressure readings have, therefore, high clinical value. The third project, aortic pulse wave velocity assessment by pulse wave analysis, is important because pulse wave velocity is a surrogate for aortic stiffness, which is an important marker of vascular health as well as being an important physical parameter for calculating central blood pressure from aortic flow. We have also shown the possibility of assessing mental stress levels by analyzing the PPG signal, which can be acquired using smartwatches. The last project on the list is the assessment of endothelial function by pulse wave analysis. This is the function of the cells lining the interior surface of blood vessels. It is clinically important since endothelial dysfunction has been shown to underlie cardiovascular disease. Further details on each project can be found in the references provided. Aortic stiffness assessment is the last project I would like to talk about. Aortic stiffness is an important marker of vascular health. It cannot be directly measured in vivo, but we can use aortic pulse wave velocity as a surrogate for aortic stiffness. The plots show the probability of overall survival and event-free survival and we can see that both decrease considerably with the increasing pulse wave velocity. Aortic pulse wave velocity is also an important hemodynamic parameter for calculating central blood pressure from aortic flow, as we have previously seen. Several clinical methods have been proposed to measure aortic pulse wave velocity from pressure and flow waveforms measured at the arterial sites shown in the sketch on the left. Typical combinations of waveforms are shown in the center. The sketch on the right illustrates the foot-to-foot method for estimating aortic pulse wave velocity using two pulse waveforms. The method calculates pulse wave velocity as the ratio of the distance, delta x, between the two measurement sites to the time delay, delta t, for the foot of the pulse wave to travel from one measurement site to the other. Distances are typically measured from surface markings, and time delays by identifying the feet of the two waves using pulse wave analysis. We have assessed the accuracy of these 4 foot-to-foot methods using a database of over 3,000 virtual subjects. Using an in-silico dataset was useful since for every subject we have all these waveforms together with the theoretical values of aortic pulse wave velocity and aortic stiffness. Our results confirm clinical observations. First, carotid femoral pulse wave velocity is a good indicator of aortic stiffness because it correlates well with aortic pulse wave velocity. Though carotid femoral pulse wave velocity tends to overestimate aortic pulse wave velocity, especially for small values of aortic pulse wave velocity, which correspond to healthy subjects. Second, brachial ankle pulse wave velocity overestimates aortic pulse wave velocity because it is related to the stiffness and geometry of both elastic arteries, such as the aorta, but also more peripheral muscular arteries. And third, carotid radial and femoral ankle pulse wave velocity do not capture the stiffening of the aorta. They are, therefore, not so good surrogates for aortic stiffness, which is in agreement with in vivo studies. There are other methods that have been proposed to assess arterial stiffness, which require analysis of only one pulse waveform. They are called single-point methods. The 3 indices shown in this slide are examples of single-point methods that can be calculated from the PPG wave measured at the finger. Data derived for all virtual subjects are shown in black, whereas red indicates data from those aged 45 years old. Using the in-silico database I showed you before, we have assessed the ability of these 3 indices to estimate aortic stiffness by looking at their correlations with reference aortic pulse wave velocity. These are the upper plots. We observed that all 3 indices correlated with aortic pulse wave velocity, with coefficient of determination values ranging from 0.65 to 0.74 for all 3 indices. This indicates that these indices may have utility for assessing aortic stiffness, in line with the findings of clinical studies. However, the R2 values for the reflection index and stiffness index were lower when using only data from middle-aged 45-year-old virtual subjects. These are shown in red, indicating that these indices may be less useful for stratifying middle-aged patients. The lower plots show the physiological determinants of each index through the relative sensitivity index I. This mathematical index indicates the percentage change in a pulse wave index associated with a change in model input parameter of 1 standard deviation from baseline. We can see that there are several cardiovascular properties, in addition to pulse wave velocity, that influence the indices, such as heart rate and stroke volume. For instance, the reflection index and the stiffness index both increased with large artery diameter. Since large artery diameter and aortic pulse wave velocity both increase with age, these strengthen their correlations with aortic pulse wave velocity across the age range. In contrast, the modified aging index was not strongly influenced by large artery diameter, and therefore performed better both across the age range and when considering only middle-aged subjects. So this in silico assessment of PPG-derived indices for assessing aortic stiffness indicates that, first, clinical studies should investigate the utility of indices over a small age range as well as over the entire cohort, indicating the potential utility of indices for stratifying patients. And second, the modified aging index may provide best performance for stratification of middle-aged patients, although this should be confirmed in vivo. To conclude, we have seen that computational flow can be used to model arterial pulse wave signals, including blood pressure, blood flow, luminal area, and PPG wave. In particular, pulse wave signals can be modeled accurately and efficiently using 1D modeling combined with 0D modeling for the boundary conditions. That's it, using reduced order modeling as opposed to computationally expensive three-dimensional modeling. In-silico datasets provide a quick and inexpensive route to initial development and assessment of pulse wave analysis algorithms across a wide range of cardiovascular conditions in a relatively quick and inexpensive manner, before carrying out more expensive and time-consuming testing and development using clinical data. We have seen the example of central blood pressure assessment, in which an algorithm was developed and optimized using an in-silico dataset. The algorithm was then verified using in vivo datasets of normotensive and hypertensive subjects. Analysis of pulse wave signals is a helpful tool for assessing cardiovascular function, for example, aortic stiffness. Modeling, and in particular in-silico datasets, enables investigation of new metrics of pulse wave analysis and their underlying physical mechanisms. Moving forward, new opportunities for analyzing cardiovascular function using pulse wave analysis are arising with the proliferation of wearable sensors. An example being the assessment of mental stress levels. I would like to acknowledge all the people in the cardiovascular research group that contributed to this research, our founding bodies, and main research collaborators. Thank you for your attention.